Welcome back. Today we're going to be exploring a very important and famous tool in mathematics known as the Fourier transform. There are several different applications and tools and properties that I won't mention here, but what I'm going to try and do is summarize some of the most common things and fundamental things that you definitely should know when it comes to Fourier transforms. And in the near future, I'll talk about some of the other applications and properties of Fourier transforms that you can use in applied mathematics, physics, engineering, and several other fields. So, since we're just going to approach Fourier transforms from an elementary perspective, I'm going to assume that you don't know anything about Fourier transforms. So what I want to do is compare to something that you probably do already know a lot about, and that's the Laplace transform. Because they're both integral transforms, but Fourier transform does have some properties that the Laplace transform does not. So I'm going to sort of compare the two in a contrast manner. So what is the Laplace transform of some function, let's say, of a single variable x? So we know that this is defined to be equal to the integral from 0 to infinity of the function that we're taking the Laplace transform of times e to the minus omega x dx, which obviously is going to map this function into a new domain. Let's call it the frequency domain. Now, when we were solving differential equations with Laplace transforms, one of the struggles that we encountered was finding the inverse Laplace transform. Now, obviously, the Laplace transform does have a convolution property, so we do have some analytical tools there to sort of help us figure out what the inverse Laplace transform is. But finding the inverse Laplace transform can be a bit tricky. But there are analytical methods out there that can do the inverse Laplace transform of some arbitrary function f omega, and one of them is the following, and that's going to be 1 divided by 2 pi the imaginary unit I times the integral from gamma plus I infinity, gamma minus I infinity of the Laplace transform of little f times e to the positive omega x d omega, where this number gamma is the real part of the complex parameter omega, right? So what exactly is this integral? Well, obviously this is what we call a contour integral, right? Because we're integrating in the complex domain of omega, which is technically quadrant 1 of your complex plane. So if you don't know contour integrals or complex integration techniques, which can be a bit tricky, especially if you don't know some of the most famous integration techniques in complex analysis, such as the method of residues, finding the Laplace transform with this method is in some sense impossible. Now there are other methods for finding the Laplace transform using methods that you probably know from single variable calculus, and one of them is the inverse Laplace transform of f omega will be equal to the limit as n goes to infinity of negative 1 to the power of n divided by n factorial of n divided by x to the power of n plus 1 times the nth derivative with respect to omega of the Laplace transform of little f evaluated at n divided by omega, right? So this is what we call the post-inversion formula. The post-inversion formula for Laplace transforms. But technically speaking, this is practically extremely difficult because you need to have a closed form representation of the nth derivative of the Laplace transform evaluated at some other parameter, and that can get quite tricky to deal with. And actually what I want to do is I want to rewrite this in a better notation. Let's call this f omega, and what we need to do is we need to evaluate this at omega is equal to n divided by x. I think that's a better way of writing it, at least to me, right? So that's the post-inversion formula, which all you have to do is find the nth iteration of the derivative of the Laplace transform, plug in n over x, and then take that limit as n goes to infinity, and you will get the inverse Laplace transform. But it's a bit messy, right? So let's just mention, at least explicitly, these two issues, right? So issue number 1, Laplace inversion. So Laplace inversion is a little bit complex. And you could, in some sense, say that the pun is intended here when I say complex. And also, another issue is that the domain of the Laplace transform is, at least in some sense, minimally. Omega is greater than, or in some sense, greater than 0. And if you were to shift that, generally speaking, it's still the right-hand side of the real line. So, what the Fourier transform does, at least explicitly, is to overcome some of these issues. So, what is the Fourier transform of a function, and how does it, sort of measure up against the Laplace transform? So, the Fourier transform of some function f will be defined to be equal to the integral from minus infinity to infinity of f of x, and we're still going to be multiplying this by some exponential decay function, but it's going to be in the complex world. So it's going to be minus 2 pi I psi x dx, and this is going to be a function of psi, which I'll denote as f hat. So f hat will be denoted as the Fourier transform of f. So what is the inverse Fourier transform of f hat of psi? Does it have a nice formula? Actually, yes. It will be just the integral from minus infinity to infinity of f hat of psi e to the positive 2 pi I psi x d psi. Right? So this actually should make you quite happy, because if you know how to do this integral, then that means in some sense you know how to do that integral, up to integration techniques, of course. Inversion in the Fourier space is definitely a lot easier than the Laplace space. And if we take a look at our domain that we're integrating over, notice that that is all of R, or in some sense all of R2, or all of C, depending on how we view it. So that is the Fourier transform of a function. Let's start looking at some analytical properties of the Fourier transform to see if it can give us any useful tools. So we know the Laplace transforms are linear operators, but are Laplace transforms also linear operators? Indeed they are. In particular, the Fourier transform of a f of x plus b g of x will be equal to a times the Fourier transform of f of x plus b times the Fourier transform of g of x. And the proof of that is actually quite easy if you just use the linear property of integrals. Another theorem that I want to mention sort of is like a scaling property for Fourier transforms. So in particular, what is the Fourier transform of a horizontal shift of a function in its normal spatial domain? So if we go ahead and look at what this is, at least by definition, we're going to have the integral from minus infinity of f of x minus h times e to the minus 2 pi I psi of x dx. So what I want to do is I want to use a u substitution here, so I'm going to be letting u be equal to x minus h, or equivalently x will be equal to u plus h, so I'm targeting that input there. So that means that du will just be equal to dx because h is just a constant. And obviously as x goes to minus infinity to infinity, shifting them to the left by edge isn't going to change anything, so you will also go from minus infinity to infinity as well. So once I perform that substitution, I'm going to have the integral from minus infinity to infinity of f of u times e to the minus 2 pi I psi of x, and x is u plus h, times du, because du and dx are equal to each other. So what I want to do is I want to decompose this exponential by distributing and factor out everything that does not have u in it. So once I do that, I'm going to have e to the minus 2 pi I psi h times the integral from minus infinity to infinity of f of u e to the minus 2 pi I psi of u du. Keep in mind u is just a dummy variable for this integral, so technically I could write it as x if I wanted to. So that means this expression here is precisely the Fourier transform of f. So what we have here is that the Fourier transform of a horizontal shift of a function practically can be viewed as a scalar multiple, depends on how you view this object, of the Fourier transform of f. Some people will view this as an amplitude change. Some people also view that as a rotation of the Fourier transform, depending on your knowledge of complex variables. Now, this property should look sort of familiar to you, at least from the Fourier spectrum, because recall that the Laplace transform of e to the minus ax multiplied by a function in the spatial domain resulted in a horizontal shift in the frequency domain, right? So we definitely do see some similar properties between the Fourier and the Laplace transforms. So let's mention just a couple more properties that I think are pretty interesting to keep in mind. So the third theorem, the Fourier transform, and this sort of follows parallel to that Laplace transform identity, the Fourier transform of the product of ax and a function is actually equal to a horizontal shift in the Fourier frequency domain of that function. So it's going to be f hat of psi minus a over 2 pi. Right? So that's pretty interesting, but in some sense not surprising. Now there are two properties that I want to sort of group together, and they are the following. The Fourier transform of the convolution of two functions in the spatial domain. So remember what this was with the Laplace transform. So the Laplace of the convolution was equal to the product of the Laplace transforms, and the Fourier of the convolution of two functions will also be equal to the product of the associated Fourier transforms. So it has practically the same exact structure with convolutions as Laplace transforms did. Also, one could say, now this property is even more interesting, that if you take two functions and multiply them in the spatial domain, then what you're actually going to get is going to be the convolution of the Fourier transforms in the new Fourier spatial domain, or in some sense the frequency domain. And that's actually, I find, pretty interesting, right? So the Fourier of the convolution is the product of Fourier transforms, and the Fourier of the product is equal to the convolution of the Fourier transforms, right? So those are definitely some properties that you definitely should be aware of when working with Fourier transforms. Now let's introduce a couple new functions to sort of work on examples with. So the function that I want to introduce so we can sort of, explore the Fourier transforms is the rectangular function. Now there are a couple notations out there for the rectangular function and also some different names for the rectangular function, but one of the more common ones is RECTX, short for rectangle. Some people also use Greek letter pi to represent the rectangular function, and some people also call this the box distribution. Also, the definition for this rectangular function may vary as well, depending on the literature and their purpose. But I'm going to take this definition, 1 on the open interval minus 1/2 to 1/2, 1/2 for those endpoints, and 0 outside of that interval minus 1/2 to 1/2. So let's just take a quick look at the graph of this function. So let this be x and let this be the vertical axis y. So our interest interval will be minus 1/2 to positive 1/2. We're going to be equal to 1 on the open interval, minus 1/2 to 1/2. We're going to be equal to 1/2 on the endpoints, and we're going to be equal to 0 everywhere else. Right, so that is the graph of the rectangular function, which obviously looks like a rectangle if I were to drop some dotted vertical lines on those endpoints. Now you may see some people move this endpoint up, you may see some people move that endpoint down, Or some people might not even define that endpoint at all on those boundaries, because in some sense the integral still stays the same from minus infinity to infinity, and I'll leave for you as a very trivial exercise to show that the integral from minus infinity to infinity of at least this definition of the rectangular function will be equal to 1. So you could in some sense view this as a probability density function for some random variable x defined on minus 1/2 to 1/2. So what happens if we scale this function just a tad bit? So let's consider the function f of x is equal to the rectangular function of some scalar multiple of x. So if that is the case, well, what is going to be happening to our domain? So obviously this is still going to be centered around x is equal to 0. And instead of going from minus 1/2 to 1/2, what you're actually going to see is we're going to go from minus 1 over 2a to positive 1 over 2a. And the height is still going to be defined to be equal to 1. The only difference is the domain is going to change, right? So that's still 1. And we're still going to have 1/2 on those particular boundaries. And this distance is still going to be equal to 1 divided by a, though, right? And I suggest you sort of work out the math to sort of verify that that is indeed the length. Nice little fraction exercises. So this obviously still looks like a rectangle. And what would the integral from minus infinity to infinity be of this scaled rectangular function? Just by using some integration by substitution, you should be able to show that this is equal to 1 divided by a. So that's the rectangular function. So why do I introduce this? I want to introduce this because the Fourier transform of this function is actually pretty interesting. And you can think of this function as just sort of like an impulse of some sense. A binary impulse. Sort of like switching on a switch and then switching it off. So what is the Fourier transform of the rectangular function? And I'll leave to you as an exercise to sort of figure out what is the Fourier transform of the rectangular function of ax. So let's use our definition. So the integral from minus infinity to infinity of the rectangular function times e to the minus 2 pi I psi x dx. So we know this is only non-zero from minus 1/2 to 1/2, so we can compress our integral down to minus 1/2 to 1/2 of, and keep in mind the rectangular function is just equal to 1 on this interval, so we can just write this as e to the minus 2 pi I psi x dx. So we're just integrating this exponential function, which is pretty nice. Keep in mind 2 pi I psi is a constant as far as x is concerned, so this is just a nice little substitution integral. So we're going to have negative 1 over 2 pi I psi times e to the minus 2 pi I psi, evaluated as x goes to 1/2 and as x goes to minus 1/2. So what are we going to get? So I'm going to plug these in backwards so I can get rid of this negative sign in front, and that's just going to give us positive 1 over 2 pi I psi times e to the pi I psi, because that 2 and those 1/2s are going to cancel. So e to the pi I psi minus e to the minus pi I psi. And that gives us that. And now what I want to do is I want to sort of rearrange these things around. I want to group my pi and my psi on the outside and my 2 and my I on the inside. And once I do that, I'm going to have 1 over pi psi times, and this should look familiar, e to the I pi psi minus e to the minus I pi psi all over 2i. And who is this function in brackets? You should recognize that as the exponential representation of sine. So we have 1 over pi psi times the sine of pi psi. Right, and keep in mind this is the Fourier transform of the rectangular function, and we get a little sine wave. And we can write this as in another way, in particular the sine of pi psi all over pi psi. And especially if you followed me in my single variable calculus, you should know what this function equivalently is represented as. So the Fourier transform of the rectangular function is just equal to the complementary sinc function evaluated at pi psi instead of psi. And some people will call this function the normalized sinc function. Normalized sinc function, right? S-I-N-C function. So what exactly does this function look like? Well, we already know what function we started with. We practically just started with this little impulse wave, right? And when we take the Fourier transform of this, what wave do we get? Well, we get a nice little dampening sine wave, where the intersections are located at -1, 1, 2, -2, and all the positive and negative integers between there. And you should be able to figure out what the limit as x goes to 0 at that point is. Everyone should know that that is just equal to 1. So, some interesting properties here. So keep in mind that the integral from -infinity to infinity of the typical rectangular function will just be equal to 1. And a wonderful little exercise if you want to sort of practice your Laplace transforms, the integral from -infinity to infinity of the sinc of pi psi with respect to psi is also equal to 1. And I think that's a very beautiful result. Also, another little exercise that I definitely highly invite you to try on your own when you have the time is that the Fourier transform of just the number 1, just the horizontal function, so one can say that it's the entire continuation of the rectangular function, but in the entire real line. This is just equal to the Dirac impulse function evaluated at psi. And in case you don't remember that, the Dirac delta function, and some people say, well, it's not really a function, then you could say, okay, then it's a distribution, so the Dirac delta distribution, where it's equal to infinity when x is equal to 0 and 0 elsewhere, right? So that is the Dirac delta impulse, or the Dirac delta distribution. So proving that the Fourier transform of 1 being equal to the Dirac delta distribution is definitely going to be important for some of the statements I make later on in this video. One of the main properties that I want to illustrate is the following. Because we know that Laplace and Fourier transforms have their nice properties, we've been using Laplace transform to solve a lot of ordinary differential equations, and Fourier transforms appear to have some advantages over Laplace transform in some cases. So the natural question is, can we use both? And the answer is, of course, yes. So what we're going to do to sort of create a nice application that sort of doesn't make, the Laplace transform monotonous, is we're going to assume now that our function, and eventually this is going to be an unknown function, is going to be a function of 2 or potentially more variables. Let's just start with 2, where we have one spatial variable and one time variable. Eventually you can increase the spatial dimensions to x, y, and z, and we'll go into, in some sense most of the time, just have one temporal variable t. So what we're going to do is we're going to define our Fourier transforms and Laplace transforms as follows. So we're going to define the Fourier transform of fxt to be equal to the integral from -infinity to infinity of f of xt times e to the minus 2 pi I psi of x times dx. So what we're focusing here is we're focused on the spatial dimension. So this is a spatial transformation, which means what we're going to have is we're going to have a Fourier transform where the spatial variable is transformed, but the temporal variable is being fixed, right? And in some sense this seems a natural choice because what we're going to do for the Laplace transform, instead of focusing on the spatial domain, we're going to be focusing on the time domain, because usually with initial conditions, usually we start t being equal to 0, and since the Laplace transform naturally starts at t is equal to 0, it's only natural to choose Laplace to transform the time domain, and hence leaving Fourier to deal with the spatial domain. So the Laplace transform of f of xt would be equal to the integral from 0 to infinity of f of xt times e to the minus omega t dt. So this is going to give us a Fourier transform, and it's going to keep our spatial variable fixed, and it's going to transform our time domain into the frequency domain, right? So again, this is a time, or some people will call it a temporal, or a time transform. So if this is the case, how can we sort of bring differential equations, or in this sense, a partial differential equation, into the story? So here is some very beautiful theorems. Theorem 1. So what is the Fourier transform of the partial derivative of a multivariable function with respect to our time variable t? So this is going to be equal to, at least by definition, the integral from minus infinity to infinity of the partial derivative with respect to time of f of xt times e to the minus 2 pi I psi x dx. Notice that this is a spatial derivative, not a time derivative, so provided that this function f and this function e are playing nice with each other, we can factor that partial derivative out with respect to time, and what we're going to be left with is the partial derivative with respect to time of the integral from minus infinity to infinity of f of xt e to the minus 2 pi I psi x dx, which we already know to be equal to the Fourier transform of our function. So we have partial t of the Fourier transform. So our variables are going to be psi and t. So we can just denote this as, for example, f hat of t psi of t. So that's the Fourier transform of the partial derivative with respect to time. So practically we just differentiate the Fourier transform with respect to time and you get the same result. So how does Fourier transforms deal with the spatial derivatives? So keep in mind we're usually only going to have one temporal variable, but we could have multiple spatial variables. So what would be the Fourier transform, at least of one spatial variable of any order? Let's assume we have partial n partial xn of our function fxt. Because we know if we take the second derivative with respect to time of the Fourier transform, it's just going to be the second derivative of time of the Fourier transform, so we don't need to sort of extend that, at least not formally. So what you will get here, and I leave this as an exercise for you because this isn't actually super difficult, you're going to have I psi to the power of n times the Fourier transform of fxt. So what you have here is a scalar multiple times f hat of psi t, right? So that's what happens when you take Fourier transforms of spatial derivatives of our multivariable function. You get practically a scalar multiple or a variable multiple of the Fourier transform. And in some sense, this is practically what Laplace transform did with time domains. Because if you recall the property for time domains, for example, the Laplace transform of f of t, its derivative with respect to time, what we got was omega times the Laplace transform of f of t minus the initial condition of that unknown function f evaluated at 0. So they obviously do share some very inherent properties with one another. Right? So that's actually pretty nice. So before I go, I just want to give you just a couple more identities for you to sort of play around with the Fourier transform before we get into the actual applications of Fourier transforms and Laplace transforms in the discussion of partial differential equations. So what are some of the little analytical calculation properties that we've discussed so far? So the Fourier transform of 1, we've already mentioned, is equal to the Dirac delta function of psi. Another little identity that I invite you to try is the Fourier transform of the Dirac delta function, or the Dirac delta distribution. That's actually equal to 1. So I find this actually pretty interesting because if we do the inverse transform of delta, we get 1. But technically, if we do just the Fourier transform of delta again, then practically we get 1 again. So that's pretty interesting. So if you do the double Fourier transform of 1, you get one back again. So we have some periodic nature of the Fourier transform, which I find pretty interesting. Another property that I invite, but this requires you to sort of explore the Dirac distribution in a little bit more detail, and that's the nth derivative of the Dirac distribution. So one can find that this is actually equal to 2 pi I psi to the power of m. So this property might not be super trivial to figure out on your own, but it's definitely extremely useful in a lot of applications in PDEs. So another property that you probably would like to know is the Fourier transform of an exponential function, let's say of the form e to the iax. So let's sort of work this out and see what it will come out to. So this is going to be equal to the integral from minus infinity to infinity of e to the iax times e to the minus 2 pi I psi x dx. So once we sort of combine those exponentials together, what we're going to have is the integral from minus infinity to infinity of 1 times e to the minus 2 pi I times psi minus a over 2 pi of x dx. So sort of why I'm showing it in this form, because this is just a shifted Fourier transform of the function 1, and we know that the Fourier transform of 1 is equal to the Dirac distribution. So if that is the case, the Fourier transform of the exponential function is just a shifted form of the Dirac distribution. So it's delta of psi minus a over 2 pi. So the Dirac distribution is actually quite natural in terms of the Fourier transform of some elementary functions. So if we know how to take the Fourier transform of the exponential function, then taking the Fourier transform of, for example, sine and cosine should not be that challenging. So what is the Fourier transform of the typical sine wave? Using this property here, I leave for you as a very easy exercise. This is going to be 1 over 2i times Dirac distribution of psi minus a over 2 pi minus Dirac delta of psi. That doesn't look like a psi. It looks like, who knows what it looks like, psi plus a over 2 pi. The Fourier transform of cosine of ax, also a very nice form. Maybe you want to pause the video and guess what this comes out to, but it's going to be 1 over 2 times the Dirac distribution of psi minus a over 2 pi plus delta of psi plus a over 2 pi. And a very interesting properties that I just want to reiterate because we've already discussed them, because these are the very important ones. Again, the Fourier transform of the partial derivative of a function of x of t. This is going to be equal to f hat of t of psi of t. And the Fourier transform of the nth derivative with respect to x of fxt will be equal to I psi n of f of hat times psi of t. Right? So, in terms of summary, what it does is it preserves time derivatives, at least by construction, because we're going to be using the Laplace transform to take care of time derivatives, and it eliminates spatial derivatives. And this will give us some theoretical frameworks and tools to solve partial differential equations in the next video. So I hope you enjoyed this video, and I'll see you in the next one. Take care.